Okay, so hello everybody. And first, let me thank you for giving me the chance to show some of our work and also some of the basics of FIP here. And so for those who are not so familiar with the geography, we are in Darmstadt here, which is in Germany. And actually, we are pretty close to the Frankfurt airport. And one of the special things with Darmstadt is it's one of the cities which has its own element, the periodic table. So the element 110, Darmstadtium. And these are just some pictures from Darmstadt. So the Mathildenhöhe, the Article quarter, this is a city castle. So if you ever come to Darmstadt, visit these places, they're the most beautiful ones in the city. This here is the Technical University, and this is the so-called Campus Lichtwiese. This is a chemistry building, and here is basically our NMR lab where we're doing our experiments with parahydrogen. So in principle, we are interested in a couple of different kind of fields. We're working with functional materials, with molecules in confinement, with catalysis, both heterogeneous and enzyme catalysis. And we're also using several different kind of techniques. We're doing solid-state NMR, parahydrogen induced polarization, dynamic nuclear polarization, also thermodynamic techniques. So we're relatively broad. Okay, so why are people interested in hyperpolarization? The answer is pretty simple. NMR is a very insensitive technique. Suppose you have 20,000 spins, you're working at 7 Tesla, then 10,001 spins are in the lower state at terminal equilibrium, 9,999 in the upper state. So there's only difference of 2 spins. On only this difference you can see in NMR experiments. And unfortunately, there are not so many parameters where you can play. You can play with a number of spins, with a B0 field, and with a temperature. And of course, there are limits. You cannot make the B0 field as large as you want. So the maximum is about 28 Tesla for commercial systems, and for very expensive commercial systems, I must say. So you cannot do this too much. Also, you cannot increase the number of spins because it has to fit in the spectrometer. And also playing with temperature is not possible, particularly when you want to work with living organisms. So for this reason, already before I was born, people were thinking about ways how they could increase the NMR signal. And nowadays, these things are called, techniques are called hyperpolarization. There are a couple of these techniques. Hyperpolarization just means brings a spin state in a population state which is very far away from terminal equilibrium. So instead of having such a situation, you want to have such a situation. And what we are using in our lab is dynamic nuclear polarization and FIP, parahydrogen induced polarization. There are also other techniques there. Okay. And so let's now talk a bit about parahydrogen. I make it relatively fast because many of the things were already covered in the first talk by Igor. And the important thing is the reason why there are parahydrogen and autohydrogen is because of the symmetry of the wave function. Protons are spin 1/2 particles. For this reason, the overall wave function must be antisymmetric when you exchange the 2 protons. And when you look at the wave function, the nuclear one, you have different terms. You have a vibrational term, which is always symmetric, and you have a rotational nuclear term, and the products they must be antisymmetric. And in a way, now it depends whether you choose which one you choose for symmetric. Other you either end up with parahydrogen or autohydrogen. Okay, so parahydrogen is where the rotational part is symmetric, which has a rotational quantum number 0 to 4. Autohydrogen is where the rotational quantum number is 1, 3, 5, and is antisymmetric. So this here is the energy level diagram, and this here is a typical temperature which corresponds to the rotational quanta there, and this is something in the order of 90 K or so. So temperatures well below 90 K, you are able to really populate these lower states. And these are the 2 spin states, the para and the auto state, which are in particular important for our FIP experiments. Okay, when you look a bit more closely, this here is how the ratio of auto and para hydrogen changes with the temperature. This is 0 Kelvin, this is 300 Kelvin room temperature. You see at lower temperatures, let's say below 30 K or so, in equilibrium, only the para hydrogen levels are populated. There's no auto hydrogen. At liquid nitrogen temperature 77 K, they're roughly 50-50. And at room temperature, basically, this is nearly this ratio, 1/4 to 3/4. If you want to look precisely, you can use this equation for calculating these ratios. Yeah. Okay. And connected now with these antisymmetric states, there's spin states which are adapted to the symmetry. So for the parahydrogen, we have a nuclear singlet state. For the autohydrogen, we have basically nuclear triplet state. And the energy splitting between these states is something like 3.6 times 10 to the 12 hertz, which basically corresponds to a J-coupling of this size. But more important, if you compare it to a magnetic field, this is equivalent to the energy splitting in a 86,000 Tesla magnet. So in other words, the thermal populations between these levels is about 3,000 to 7,000 times higher than with typical magnetic fields. Okay, now let's come to FIP, already shown by Igor. FIP originally was a chance discovery, so people didn't realize what it was. They found some funny antiphase signals, which were called Mandy effect. And the thing really started getting interested when Dan Weitekamp and Bauers showed in this paper the theoretical possibility of using symmetry of wave functions for hyperpolarizing spins. And they first showed it theoretically, and then there were a couple of experimental demonstrations. There was the Pasadena and the Alta experiment. So one was hydrogenation reaction inside of the magnet, the other was outside of the magnet, and about 20 years later, there came the Saber, where the hydrogenation reaction no longer was irreversible, but it was reversible, which means basically only an intermediate state was hydrogenated. Okay, so these here are these original papers. This is the Pasadena paper from 1987. This here is the Altadena paper from 1988. And this is the original Saber paper from 2009. Now, I want to show you a bit what kind of experimental setup we are using in our lab and how it has evolved in the course of the time for FIP experiments. And the first thing what you need, of course, is a source of parahydrogen, unless you want to work with this very tiny difference at room temperature. And the easiest way when you're not in Siberia is to take a bucket, you have some liquid nitrogen in the bucket, and then you have a kind of a U-tube. This U-tube is filled either with charcoal or with iron oxide. You put hydrogen gas inside, wait for some time, and then you have created parahydrogen. And when you have the parahydrogen, you can do the reaction, which means you're bubbling to your reaction solution. And when you're doing it outside of the magnet, afterwards you should run fast to the magnet, throw it inside, and make an NMR experiment. And then you get the typical line shape of a FIP experiment, usually with strong enhancement. This is how we started this whole business in about 2009. This is also the most easy way to find out whether you have parahydrogen present or not. Since you want to do NMR anyways, just use something which is easily hydrogenatable, make the reaction and check whether you get a FIP signal. When you get a FIP signal, you have parahydrogen. You can also use this then without fancy catalysts. So this was something which we found by chance, that you don't need complicated catalysts. It's sufficient to have just the metals in solution to do some kind of FIP effects. And in other words, also you can say you can use parahydrogen-induced polarization experiments for detecting leaching of catalysts. Then we also started thinking about doing it at lower fields. So this here were our first ventures in the field of low field or benchtop NMR together with FIP. This was a so-called Bruker time domain analyzer, which means a spectrometer which is so broad with the line width that it's mainly used for relaxation measurements, but you can do it nicely with FIP. And if you do the pulse sequence like this one, for example, you also can convert antiphase lines into in-phase lines more or less and get relatively decent spectra. Doing this handmade FIP experiments is nice, but it has a big problem. It's a big problem. It depends how fast you're running, depends how you're shaking, and it's very hard to control it, and you don't have good reproducibility. So after some time, we got just tired of doing the hand-made FIP, and we were thinking how to automate the whole setup so that everything is run under computer control, and hopefully also with better reproducibility of the results. And so this was a basic idea. We want to have our control with the gases, it's controlled by the computer. Here's a mechanism with a reaction. This is a photo how the systems start to look like. And the whole setup was built in about 2017 by Alexei Kiryutin, who then was a guest in my group, who gave a talk yesterday, and Kritzauer as part of her PhD thesis. So what you're seeing here are electronic valves which are open and closed, gas flows. These are control units, and the whole thing is controlled by a computer. And you still see our bucket here for creating the parahydrogen. And with this setup, we were able to have a reproducibility of about 1 to 2%, so which is much better than the 30% or worse, which we had with the previous handshaking setup. The next steps then was getting more parahydrogen. Getting more parahydrogen means you have to go to lower temperatures. So we bought such a commercial parahydrogen generator, which works with about 20K or so. And with this, you get more than 90% enriched parahydrogen. This was installed by Stefan Knecht, who was a postdoc in my group at this time. Finally, then the last evolution of the setup was that we thought, okay, we want to combine high field and benchtop NMR with FIP, and we want to be able to switch between a high field spectrometer, 500 megahertz spectrometer, which we're seeing here, and a benchtop spectrometer, which we're seeing here, which was part of the PhD thesis of Francisco Theis. Okay, and these are just some examples of this two-field setup. This, for example, is a self-transfer to carbon-13. This is a pulse sequence. This here is done at the high field spectrometer at 500 megahertz. So we get about 0.91 polarization. As this here is done at the low field spectrometer, so we get about 0.64% of polarizations experiments. And while this here is a time saving about 1.5 years, this here will take 60 years to get the same signal to noise enhancement. Okay, now I will give you a very, very short tutorial how you can do some very simple simulations of FIP experiments. And so what you have, of course, is three phases. The first phase is just a chemical reaction, where you're bubbling the parahydrogen to the reactant solution, for example. Then perhaps you have a field change. For example, when you are going from the Albertina experiment from outside the magnet inside of the magnet, so BR is a reaction field. B0 is the field inside of the NMR magnet. And finally, do an NMR detection, measure the signal, and calculate the spectrum. When you want to calculate it in a way, so you have to follow these 6 steps here. First, you just have to set up some spin operators for doing the calculation. You should calculate this operator for a detection pulse. You're calculating the density matrix at the end of the reaction. Then you change from the reaction field to the detection field. You apply your pulse, and you calculate the spectrum from the density matrix. So when you do this in a sequence, so we're starting here with the density matrix of parahydrogen. We are getting the density matrix at the end of the reaction, changing the field if necessary. We're applying our pulse. We have the density matrix after the pulse, and from this then we can calculate basically the FID or the spectrum, however we want to do it. Now, so the first thing is we have to decide about what kind of base are we using for doing these calculations. And the most easy base is just using the Zeeman interactions, the nuclear Zeeman functions. And here we have the typical 4 spin operators, Px, Py, Pc, and Pe is a unity operator of the spin 1/2. And from these operators, then we can calculate the operators in a coupled spin system. Since we only have a 2-spin system, we only need to calculate six operators, namely the I1, Xi1, Yic operators for the first spin, for the second spin, the I2X, I2Y, I2C operators. There's a relatively simple way how you can calculate these operators. So in a way, what we're using is so-called Kronecker products. This Kronecker products is the general rule for this. It just tells you, so here you put in, for example, Px, here you put in Pe, then you just calculate the scheme at the end up then with this operator. And in addition to these six operators, we also would like to have the total spin operators, which in the two spin cases just Fx, Fy, and Fc. Okay, finally, we need some detection operator, which we're using for measuring the magnetization. The detection operator is just the F plus operator, which is just I1 x plus I2 x plus I times I1 y plus I2 y. So we can calculate them from those here. Okay, now we also need a pulse operator. In the case of spin 1/2 and two spins, this pulse operator is relatively simple. So this here is the general form for a Y pulse. If you put in just that we just have two spin 1/2 coupled, so we can calculate analytically the matrix and also write it here. So this basically, this operator describes us then the pulse which we can have to apply. There are two special cases. This is the operator for the 90-degree pulse. This is the operator for 45-degree pulse. And the nice thing is, since we're using Fy here, all the numbers are real numbers. We don't have to work with complex numbers here. Now let's do the reaction. So the reaction is, we have some substrate plus a parahydrogen. It goes to the product. How do we describe reactions? A reaction is a so-called sudden change of the Hamiltonian. Sudden change means that the spin density matrix is preserved under the reaction. So you can think like this. This is spin. Spins are very slow and the reactions are very fast. So the spin doesn't feel the time during the reaction. The spin only feels that something has changed after the reaction. Before the reaction, we start with a singlet state. After the reaction, the singlet state can evolve under the Hamiltonian at the polarization at the reaction field, which means after some time t, we will have usually some change of the density matrix. The thing is, reactions take some time. So typically we're bubbling, let's say maybe 5 seconds, 10 seconds, 15 seconds. Some spins have reacted already at the beginning of the time, others react later. So they all will have different starting positions. And at the end, we have some kind of an average of these different starting times. And the nice thing with this average is it's relatively easy to find it. If we just say that the time is long enough, then what we find is that only the diagonal elements of the density matrix are populated in the eigenbase of this Hamiltonian, and the off-diagonal elements just disappear. So you can just use this tool. You have to be careful if the degenerate levels are present in larger spin systems, then things are getting a bit more complicated. Okay, now let's just apply this very, very simple model to our two experiments. First, let's do the alter data experiments. So here we have our reaction field. Then from the reaction field, we're going, after the reaction is bubbling, we're going inside of the magnet. So this here is the typical scheme that we have one line absorption, one line emission. First, now the question, of course, is what is the reaction field? The answer is it depends a bit where you are. So this is just taken from Wikipedia. This is the strength of the Earth's magnetic field for different locations on the Earth. And you see typically the average value is something between 30 and 60 microtesla. So it's definitely not zero. Then it depends a bit on the lab where you are. When you have a shielded magnet, which is close, then in a distance of about 1.2 meter, you also have a field of about 50 microtesla. So basically, which is on the same order as the Earth's magnetic field. So in a way, the field where the reaction is done is more or less a sum of the Earth field plus local fields. Now, what does it mean for the interactions which we're dealing with? When we just look at frequencies at 50 microtesla, then we find the Lambda frequency of the proton is about 2100 hertz. 2100 hertz, when we look at typical chemical shift differences in proton, it tells us typical chemical shift difference on the order of 100ths of a hertz. So definitely something which we can neglect, especially compared to the typical J coupling, which so we will definitely end up in still in A2 spin state. However, of course, we cannot neglect scalar couplings to other nuclei. Suppose, for example, your proton is sitting on carbon-13 nuclei, then there the J coupling is something about 500 hertz, so it's larger. So in a way, not only by chemical shift differences, but also by hidden-pair scalar couplings, you can break the spin symmetry and can create more complicated Fib pattern. But the nice thing is we can forget about chemical shift. The other thing is if we want to do Zwölf experiments, which means experiments where the reaction field is much lower than 50 microtesla, ideally, for example, 0 Tesla, then you have to shield external fields. And I think you've already seen a couple of pictures in this conference that people, for example, use mu metallurgical shielding for removing these fields. Okay, so now let's just sketch how the calculations is done. In the case of the Altadena experiment, the density matrix before the NMR pulse is just everywhere 0 unless the one level which is populated. We're assuming this is a weak coupling Hamiltonian, so this is two chemical shifts. This is scalar interaction. This here is our detection operator. And then we can calculate the density matrix after the pulse. And when we compare our NMR signal is given just by the trace of the density matrix and the detection operator. Now, when you look at the detection operator, you see only these 4 elements here are 1, but the rest is 0. So this means that also from the density matrix, we have 4 contributions to the signal, which are shown here. And when you write down, then here's the amplitudes of the 4 lines, which we're getting as a function, in this case, of the pulse angle. And we also can plot this. So here is shown the pulse angle. This here is the amplitudes of the 4 lines. And you see basically how they are changing as a function of the pulse angle. And when you look at the spectra, so all spectra normalize the unity, otherwise the Boltzmann signal would be much, much lower than here. Then you see, for example, this is a pattern for Altadena with a 45-degree detection pulse. This is with a 90-degree detection pulse. So in other words, when you make the cut here or when you make the cut there. Now we can place the same guy with a Pasadena experiment, where you're expecting this to 2 antiphase pairs. In this case, the density matrix has these 2 elements populated. Once more, we're doing the calculations. This here then are elements which contribute to the signal. These here are amplitudes. And this here then is basically how the amplitudes depend on the pulse angle. And we see, for example, the biggest signal we get for pi over 4, pi over 2, 90-degree gives no signal. And these here then are the simulated spectra under these conditions. Okay, now let's give you just some very short examples of how we're using the Fib together with biomolecules. And we're interested in peptides, and in particular in peptides which have some biological functions. Why are we interested in peptides? The reason is very simple. I like to play with Lego, and peptides are like Lego. In a way, you have a very simple chemistry where you can build these peptides from the natural amino acids or also from just some Fib-labeled amino acid. And in other words, you can basically create arbitrary kinds of systems which you want to study. And of course, you need a Fib label. The most simple Fib label would be just a propagyl group. And on the side chain, you have a triple bond. When you have this propagyl group, you can do 2 hydrogenations. Both hydrogenations should give a Fib signal. When we started, our first results were pretty modest. So we got enhancement factors of, say, 10 or 20. Then we started working with larger peptides. So this was about 12 years ago. So this is a decapeptide, and then we found already an enhancement factor of about 40. And then we thought, okay, until now we use toy systems. Now let's use a system which has really some biological function. So we started to collaborate with Harald Kolmer's group on the sunflower trypsin inhibitor number 1. First, we wanted to label it also with our propylglycine. This did not work, most probably because the catalyst was blocked because the side chain was just too short. So we said, okay, let's use larger side chains. So instead of using propylglycine, we went to propyltyrosine, and there the amino acids you can hyperpolarize, but when you work with peptides, the propylglycine works much better than the propyltyrosine works much better than the propylglycine. And then we put it inside of the large peptides, SFTI1, and also there it worked. And then about 11 years ago, when we did this, we had enhancement factors of 70. So we were already very happy and thought, okay, can we optimize the whole thing now? And this was also part of the work of Gerd Sauer. So after optimization, we arrived at enhancement factors of about 1,200. And with these large enhancement factors, you can also now do more complicated NMR experiments. For example, ultra-fast 2D NMR detection. Ultra-fast NMR means just that you can measure a 2D spectrum in a single scan. This Alexander colleague did these experiments, and he programmed first a pulse sequence, and then he and Gerd studied the SFTI. This is an ultra-fast FIB-COSY, ultra-fast FIB-TOXY. You see very nicely a single scan, you can get the 2D spectra. We also played with the concentration, and we found we can go down to about 300 micromolar solutions and still very nicely see the hyperpolarized signals in a single scan of the FIB enhancement. Okay, now we started, okay, let's do some more drugs. And so this here is basically octreotide. Octreotide is a somatostatin mimic, which is used in various therapies. And we did a FIB labeling of this one with the propyltyrosine. And also this worked very nice. So we get enhancement factor about 1600 or so. Or here, we can also do some poison. This here basically as part of the rattlesnake poison, the eptifibatide. So here we did two different kinds of labeling. One labeling for FIB, and this is with a similar chemistry, also labeling for EPR and DNP. Both were successful. So in a way, we can create peptides relatively easy labels, which we can label compounds for EPR, DNP, and FIB. So we see it's really like playing with Legos. And at the end, then we were wondering, can we also do much bigger systems? So we started working on a mini protein, which was once for collaboration with Olga and Harald. This here is a mini protein, NQTI. It's biologically active, so it still has its function after the FIB labeling. And we got enhancement factors depending what kind of labeling we use, but 500 to 1000. So also this here worked very well. At the end, then we said, okay, can we also go to really big molecules? And so this was a collaboration with a group of Christina Thiele. They studying a biopolymer, which is just a homopolymer of this amino acid. And we tested whether we can use this with FIB. And also this worked very well. So in a way, you can also do FIB basically on really large molecules with 230 kilodaltons. So he uses a FIB enhancement, and he was part of the PhD thesis of Franziska Theis. Okay, and with this, I'm also at the end. So these are basically my funding sources. This is a group about 2 years ago. Nowadays, it's reduced to a bit less than 1/3 of this size. And with this, I'm at the end. Thank you.
Gerd, thank you very much for that incredible educational talk. There is one question in the chat. So it's a general question about FIP and iridium chloride and how the heck do you say this? Rhodium chloride. There you go. Sorry, the physicist in me is a little bit worse than chemistry. Is the FIP producing catalyst homogeneous in this system? Or maybe these salts are in part reduced to metal nanoparticles which produce FIP heterogeneously?
Okay, so I would say basically it's just homogeneous catalysis. And so what we did is we had first worked with immobilized catalysts, and there we found then that most probably something was fishy there, and for this reason we just used the salts as a control experiment, put the salts in solution, did the FIP experiment, and we really got then the FIP enhancement from the atomic or ionic catalyst and not basically from some kind of nanoparticle which had formed there.
Great. Thank you so much. Are there any further questions from the room? Thank you again for an amazing educational talk.